Good day and welcome back. This is our third video discussing vectors. So in the previous two videos, we've gone over different perspectives of the vector, first geometric, then analytical. I'd like to finish up this discussion by going into some of what we might think of as the basic properties, things that we will use multiple times over and over again throughout this course. So the first thing is standard basis vectors. So in V3, the standard basis vectors are the vectors I, which is 1, 0, 0, j, which is 0, 1, 0, and k, which is the vector 0, 0, 1. And the reason we call these things as standard basis vectors is because each vector in V3 can be expressed in terms of the standard basis vectors. So we can express each and every vector in V3 in terms of I, j, and k. And let me illustrate this. If we start off with some arbitrary vector with three entries, so typically we think A1, A2, A3. And if we use properties we discussed in the previous video, we could easily think of this as being three vectors added together. A vector containing that first coordinate or component, a vector containing the second component, and then a third vector containing, you guessed it, the third component. And then furthermore, thinking about how scalar multiplication works, we could pull that A1 out of the first vector and have a 1, 0, 0 left over. We could pull the A2 out of the second vector and have a 0, 1, 0 left over. And pull an A3 out of the third vector and have a 0, 0, 1 left over. And hopefully from looking above, you immediately note that that first vector is I, the second vector is j, and the third vector is k. So given any vector with three entries, so a1, a2, a3, we can immediately break it down and do its components. a1i plus a2j plus a3k. The next kind of basic property related to vectors would be the length of a vector. And the fancy word that we will use for length is magnitude. And the notation that we will use for it is just absolute value of the vector. And in words, we would just say the magnitude of v. And let's just build up to this definition. If you have a vector containing two entries, so a comma b, then the magnitude of v is the square root of a squared plus b squared. So that is, it's the square root of the sum of the components squared. And that pattern in words extends regardless of the number of entries that we have. So if we have a vector with three entries, the magnitude of v would be the square root of the sum of the components squared. A squared plus b squared plus c squared. And the other property I want to note here is if you want to find a length of a scalar multiple, we can go back to exactly what we said in our first video. We take the absolute value of that scalar and we multiply it by the length or the magnitude of the vector. And note in terms of our new notation and language, we would have the absolute value of the constant k, and we're multiplying that by the magnitude of the vector v. And note the context and the notation make it very clear what type of quantity we're dealing with. That arrow over the vector indicates a vector, and just a quantity by itself indicates a constant. Now, in terms of vectors and magnitudes, something that we will encounter frequently at various portions in the course is the need for a unit vector. And a unit vector is very simply put a vector of unit length or having length 1. And to see some examples of unit vectors, it turns out that we don't have to look very far. as the vectors I, j, and k above are all unit vectors. And if you're unsure why that's the case, note if we wanted to find the length of, let's say, I, that would be the square root of 1 squared plus 0 squared plus 0 squared, which is the square root of 1, so it has unit length. And a typical question that we might be asked is if we're given any vector, let's call it A, as long as it's not the 0 vector, because the 0 vector has no direction, what is a unit vector in the direction of A? And I'm just going to go ahead and write down what the formula is, and then we can explain why this is the case. So the unit vector in the direction A, so if A has a name, I'll typically call that u sub A, and it has the same direction as A, but to make it a unit vector, what we have to do is kind of scale it appropriately, that is multiply it by the right scalar quantity. And that scalar quantity would be 1 over the length of A. So the unit vector in the direction of A is 1 over the magnitude of A multiplied by A. So this helps us get the proper length. We preserve the direction. And just to give kind of a small note here, you might say, well, why is that a unit vector? Well, let's just double check. If we find the magnitude of u sub A, we want the magnitude of a constant times a vector. And if we look up just a little bit here, it's really this third property above. We can take the absolute value of that constant, which is already positive, so it turns out the absolute value is not even necessary. We can just pull that out front in a sense. And then we can multiply that by the length of A. And here those quantities cancel, and we're left with simply a unit length. So let's look at one more example dealing with unit vectors and magnitudes. And if we were in class discussing vectors, this is usually a topic I'd spend about a full 50-minute period on. Towards the end, we'd get to the point where I'd ask you all to spend a few minutes working on an example. So for this vector v equals 8i minus j plus 4k, pause the video, take a few minutes, determine a unit vector in the direction of v, and then go beyond that to find a vector in the direction of v, but with length 5. Okay, so assuming you've paused the video for a few minutes, and if not, really do that now, I can first think of v in component form. So this is 8 minus 1, 4. If I want to find a unit vector in the direction of v, what we need is first the length of v. So the length of v would be the square root, where we sum up the components squared. So 8 squared plus 1 squared plus 4 squared. So this would be the square root of 64 plus 1 plus 16, so 81, and the length of v is 9. And what this is telling us is that a unit vector in the direction of v is given by the scalar 1 over the magnitude of v times v. So that would be 1/9 times the vector 8 minus 1, 4. And I am perfectly happy with you leaving the vector exactly in this form. It's also perfectly fine if you'd like to throw that 1/9 into each of those components. But regardless of how you represent it, we have this unit vector in the direction of v. And let's take it one more step further. Now that we have this unit vector in the direction of v, let's also find a vector in that direction with length 5. And remember, if we know the direction, we could simply multiply that unit vector by the proper constant to give it its length. So in this case, that vector going in the direction, same direction as v with length 5, I'm going to call that as v sub 5. You don't have to call it that, but this would be the scalar 5 times that unit vector in the direction of v. So this would be 5/9 times the vector 8 minus 1, 4. And in general, if you'd like to find a vector of any length going in the direction of v, you just take that desired length and you multiply it by the unit vector in that direction. So that finishes up our third video. What remains that we'll hit in a fourth video is just kind of one application dealing with vectors. So stay tuned and take care.